Yeah.
Did you get it? Okay. I didn't hear the beep. It always worries me when I don't hear the beep, but it's just a coincidence of me. It's got the red dot? Okay. I trust you. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray that you'd give me energy to say interesting things today, Lord. Amen. All right. First of all, we should look at how to do implicit differentiation. And so I'll discuss it here using differential notation. I think this is a useful discussion. And so this is my section 3.3. I mean, I am not really using a book at the moment, so it's not like I'm going to say, oh, which is also section blah and blah. No, I mean, we're stuck with me at the moment. Now there is a chapter on advanced calculus in the book we're going to use, and so some of these things will appear again there, except probably more correctly. Let's see here. So G1 of x1 through xm at the moment, and y1 through yn at the moment equal to k1. I say at the moment because I think I changed the numbering when I get into the next section on manifolds, implicit or otherwise. But I'll stick with what's written as to not create chaos. So the point is, we're looking at these equations, okay? And we've got n equations. And how many unknowns?
M plus n.
Right, m plus n unknowns. Very good. So here's what we got. We got n equations in m plus n unknowns. So intuitively speaking, you're starting with m plus n degrees of freedom, all right, in this object, and you're constraining it by n equations. So intuitively, you'd kind of expect to be whatever's left over would be m-dimensional, right? That's the basic sort of overriding idea. Now, of course, that intuition comes from linear algebra. And I'm saying that it's still true in some sort of nonlinear context, at least locally. And let me kind of flesh that out a little bit more explicitly. So what we do is we can take the total differential of each one of these equations. All right? So like dg1 is going to be, partial 1 g dx1. Oh, bad notation. Sorry. I guess I've used my numbering doesn't allow me just to, what? Partial g partial x m dxm plus partial g y1 dy1 partial g partial y n dyn equal to, well, 0, right? And then the total differential of G2, what's that look like? And you see I missed something, right? Yeah, in fact, let me not write this again because it's really not that interesting. We can take the derivative of the, let's say, ith component equation, right? And that does what? That I need to adorn it with a, if I'm thinking of this as a scalar equation, I'm missing an index, right? We could also think of it as a vector equation. That wouldn't be wrong. We could take the total differential of a vector valued function, and like this would be totally legit if I just think of all of this collectively basically being g of x comma y equals to k, You could take the differential of the vector valued thing and look like that. These would be vectors then, But let's not be quite out there so much. Let's say that this is the ith component. Then there's an I here, there's an I here, there's an I there, there's an I there, all right? And that's for I equals to what? 1 less than or equal to I less than or equal to n, right? So up here, I should really emphasize that our initial starting point, yes, we have m plus n equations, and these are very likely nonlinear, right? These are nonlinear equations, right? And what are the unknowns? The coordinates, x1 through xm and y1 through yn, right? So the universe in which this is happening is essentially, you know, in Rm cross Rn, right? That's the context. But now, after we take the differential of the system of, system of constraints, what do we have? We have m plus n, right? M plus n equation. I'm sorry, I'm an idiot. M plus n unknowns, right? But the unknowns, like up here, the unknowns are x1, xm, y1 through yn, right? Down here, the unknowns in this system of equations are dx1 through dxm, dy1 through dyn. And you notice that we have n equations still, but what kind of equations are they? They are linear. So taking the differential of a system of nonlinear equations produces a corresponding system of linear equations for the differential. And essentially the content of the implicit function theorem is to say that if you can solve the system of linear equations and the differentials for some subset of the differentials as a function of the others, right? If you can do that, what that means is that you can find functions for those dependent differentials, if you will, that write the remaining variables, that they express those dependent variables, corresponding dependent variables as functions of the remaining independent variables, which correspond to the independent differentials. Yes, Daniel? What? Are you just going through? What?
No.
Nothing? It seemed like something. This is all very confusing to me. Okay, so, but that, I mean, the theorem proves that there exist these functions which we can solve for some of the variables in terms of the others, right? But in terms of an intuitive calculation to remember the result, pragmatically, when can you find one variable in terms of another if you can take this system of differential equations and solve for some differentials? Like that's a way to remember the implicit function theorem, independent of, whatever notational setup you're using. Now, if I rewrite this, I can rewrite this briefly just to make sure I kind of complete the thought here, which is that so we can express let's see here, like basically we can write that as partial g, partial x, well, sorry, a little bit better. Partial x1 g, partial x2. Now I'm thinking of these vectors of partial derivatives, right? Or the partial derivative of the vector value function g. So these are n vectors. So if I can take this system of linear equations, I can rewrite it like this. How many y's did I have? M? N? I forgot. N, right? N. Better be n, right? Because that means that this is equal to 0, right? So we can rewrite that system of differential equations. I'm sorry, not differential equations. Equations involving differentials. Be careful. Unfortunate language, yes.
Is there any reason why you didn't write partial y?
No. I blame Daniel. That's probably not entirely inaccurate. I mean, so this gets very old, but you know what I mean by these. I gave these names last time. This is, let's say, partial g partial x, right? And let's call this thing partial g partial y. That's a good notation here, thinking of x and y themselves as sort of vectors of variables and just, you know, collecting the notation down a little bit better. And we can think of this as being dx vector, right? And dy vector, since I haven't used vectors anywhere yet. So basically we're solving this equation, partial g partial x dx vector plus partial g partial y dy vector equals to 0. And the idea, again, getting back to the fundamental counting, is that we have a universe of m plus n variables. We've got n constraints. I'm sorry, excuse me. What?
That's not it, right?
Oh, n constraints. So that means we have m unknowns left over. Right. Sorry. There's a duality here that was messing with me. It's fine. Let me just keep going. So the point is, this is a square matrix. This is an n by n matrix, right? So if that's invertible, then we can solve for dy. And dy vector will be equal to minus partial g partial y matrix inverse times partial g partial x dx vector. And this right here actually tells you how the derivatives of the dependent variables depend on the independent variables. So we have these differentials correspond to our x1, x2, xm independent. All right, and then the implicit function theorem says that y1, you know, it's some function f1 of x, of the x variables. In y2, it's some second function of the x variables, and so forth and so on. The, you know, nth y, again, it's some function of the x variables. The existence of these functions is given to us by the implicit function theorem formally. But actually, the funny thing is, this calculation really is the heart of the proof of the implicit function theorem as well. This starts the iteration, and you know, this you find. Basically, you solve for the first function, then you plug it back into this again, and you just keep doing it over and over again, just like Newton's method, and that's basically the proof. So what I mean here by saying that these are, what do I mean when I say that these are, local solutions? That means that when you plug these back in, we have that g, right? G of if you will allow me x comma f of x, right, is equal to k, where I'm thinking of this collectively as being y vector equals to f of x. If you want to put a vector on the f, if it bothers you, if you'd like to put a vector on the f, feel free, go nuts. It's all good. All right. So, what condition is needed to solve for y? What's the condition needed to solve for y as a function of the x variables locally? Simply that this particular matrix of derivatives is invertible, right? Let's see here. Example. Yeah, k is a vector. K would be like the k1 through kn. Again, if you'd like, adorn appropriately. Let's see here. So I have a bunch of examples in the notes. I don't want to cover all of them. I need to pick a good one. Is there a particular example you guys would like me to work through? No? All right, let me try to pick one that's... So let's see here. This one's not too scary, and it kind of illustrates the idea fairly well. So if we've got x plus y plus z plus w equals to 3, and I think I did some of this last time. Maybe I shouldn't do this. X squared minus, I'll try to go fast, 2xyz plus w cubed equals, I think I actually did this last time, right? More or less. So if I wanted to, but maybe this time just to drive this point home, let's see here. So you take the differential of both equations, you got dx plus dy plus dz plus dw is equal to 0. We've got 2x dx, oops, I can't differentiate. 2x minus what? Minus 2yz dx, right? Minus 2xz dy minus 2xy dz. Why did I make this so awful? I guess it's not too bad. 3w squared dw, right? And then you can pick, do you want to write x and y as functions of z and w? Do you want to write z and w as functions of x and y? Tell you what, I'm going to write z and w as functions of x and y, because that just seems kind of like a natural thing to do. So we'll try to z equals to z of xy, right? And w equals to w of xy. We're gonna attempt to, let's find partial derivatives of z and w, right? As above, as functions of x and y. Not that the derivatives are actually going to be in terms of x and y, but I mean z and w as functions of x and y. I'm sorry, bad language. So what I need to do is I need to isolate the dz and dw. So I got dz plus dw is equal to minus dx minus dy, right? This one, I've got minus 2xy dz plus 3w squared dw. And I just take all the xy stuff to the other side. So I've got 2yz minus 2x dx plus 2xz dy. I'm trying to solve for, so basically here, my dy, quote unquote, all right, in the implicit function theorem, pay no attention, pay him no mind, is dz dw in my current way of thinking, okay? I'm trying to solve for that. So that's pretty easy 2 by 2 matrix stuff, right? This is 1, 1, minus 2xy, 3w squared, dz dw. Just a warning, Daniel, if you distract me and make me do something wrong, I'll just stay longer. Let's see here. Students are like, no! Daniel, behave. Let's see here. 2, I can't do math. See, Daniel, it's already begun. Goodness gracious. Anyway, you know what I'm trying to do here, I think, but let me do it. So this is minus dx minus dy, and this is, 2yz minus 2x dx plus 2xz dy. All right, so there you go. We get that dz dw is equal to, the inverse matrix of this, which is what? What's the inverse of that 2 by 2 matrix? So we're looking at a 3w squared plus 2xy. That's the determinant of that 2 by 2 matrix, right? Flip the diagonals on that guy. Put minuses on the off diagonal. There you go. There's your classical adjoint transpose inverse formula for the 2 by 2 case. So then we got to multiply that by this monstrosity. I mean, it's not too bad, really. All right. Okay, so then we get what? We get, oh, yeah. I'll leave that out front. No point in writing that a bunch of times, right? And so with multiplying that times that. Why am I actually writing this out? What is wrong with me? Oh my goodness. See, Daniel's complaining that I tell the students the answers. I said, yes, I tell the students the answers, but I tell them so many answers that it's still hard, right? I hope they do. That's the idea. What, you try not to listen to mommy's answers so that you don't remember them because that's cheating? Yep. I said, yep. Okay, so let me just, from this I can extract something like dz, all right, here it is. dz is equal to what? Stuff. I'll do the denominator, that's easy. 3w squared plus 2xy dx. Stuff. Denominator's easy. dy, all right. What goes in the numerator? Well, we can figure it out, right? We got a what? We got a minus 3w squared oh yeah, plus 2x minus 2yz. Anything else? That's it. So over here we got a minus 3w squared from that, from the dy, right? And then what else do we have? Minus 2xc. The meaning of these coefficients, what this is partial z, partial x, holding y fixed. This has the meaning partial z, partial y, holding x fixed. So if you look up in here, this contains, partial z, partial x, partial z, partial y, partial w, partial x, partial w, partial y, holding y fixed, holding x fixed, holding y fixed, holding x fixed. They're all implicitly in that. We just have to, we read them off as coefficients. This is not something you saw in Calculus 3, right, Travis? Right?
I mean, I know how it works based on what we talked about this morning.
Oh my goodness, I hadn't even thought of that.
I just couldn't read the red over there because my eyesight's on.
Oh, I'm so sorry.
Don't worry about it.
But so what if I just gave you this, right? The way I teach Calculus 3 students to do these kinds of problems is I say, okay, if you're going to calculate, partial z, partial, let's say x, holding y fixed, right? What do? You pick one of them, right? Like this one, if I differentiate this with respect to x, it gives me 1. If I hold y fixed, partial y, partial x holding y fixed is 0. Right? But this is partial z, partial x, which is what I'm after, and then plus partial w, partial x holding y fixed, which is something else that is not what I want. So this tells me, you know, like partial z, partial x holding y fixed is equal to minus partial w, partial x holding y fixed minus 1. And then I have to go use this relation to get the relation of partial w, partial x, and plug that in there. And then I have to, after that's done, I have to solve for partial z, partial x. I mean, that's how you do these kinds of partial differentiations without matrix stuff. The context where this would come up is like you've got a model, right? Like you're trying to find derivatives of some state function or something, and then you're looking at it as it's constrained by some other relation, right? It's when you're looking at how something changes when it's subject to another constraint. You end up with these kinds of issues, right? And to answer the technical questions that underpin them, it's a careful application of the implicit mapping or implicit function theorem. Okay, anyway, I think that's enough on this. Let us move on. I have like another half dozen examples in the notes which elaborate on, like, in calculus books, most calculus books, they will just write this, right? Like very, very popular homework questions, this, partial p, partial v, partial v, partial t, partial t, partial p equals to minus 1. Yeah, haha, we tricked you. But the thing is, this notation in my view is like substandard, because what this really means is partial p, partial v holding t fixed. This is partial v, partial t holding p fixed. And this is partial t, partial p holding v fixed. So these expressions live in wholly different sort of mathematical universes in terms of how we're writing one thing in terms of another. I mean, this is a very bastardized expression. It is, you know, p is a function of v and t, v is a function of t and p, t is a function of p and v. I mean, it's all intertwangled.
That's all over the thermodynamics.
Yeah, oh, and yeah, it's unavoidable. In thermo, it's like, that's so much of what it is. Okay. So, what's a manifold? I need board space. So what do you guys think? What should a So I will try to describe to you in the time that remains, which hopefully is a fair amount, are ways we can look at curved surfaces, or, you know, let's see here. Let me just some pictures. So let's talk about submanifolds. And I won't use that word too much, but I'll actually just say manifolds inside, you know, our, well, let me say our Q, because I don't want to commit. So what are examples of manifolds? I mean, you've got curves, right? You've got surfaces, all right? Although at the moment, this isn't really accurate. Well, no, it's fine. What is it, Daniel? Well, then go. That's here. You have, now this is something you probably haven't thought as much about, but solid things could be manifolds, all right? Now, to be picky, I'm not being super critical about edges at the moment, all right? But the question is, how do you, I mean, there's one of the things about a manifold is it's some kind of space inside RQ, right? And the thing that we don't allow, like one thing that wouldn't be a manifold in our view, would be something like, you know, I take this line, right, and then I just attach a disk to it here. Just stick a disk on it like that, right? Or I'm going to take this surface, and then, you know, I'm going to build a building on it, and I'm going to call that a manifold. You know, like, no, that's no, you can't do that. the thing is, the curve here I'm talking about it's one-dimensional. This is a one-dimensional manifold. This is a two-dimensional manifold, right? This over here is a three-dimensional manifold, right? And these are some sort of admixture of those two things, right? I mean, it's got a one-dimensional piece, but then it's got this two-dimensional piece. That's not something that a traditional idea of manifold allows for. This idea of manifold, it insists that there's something called dimension, right? And that's well defined for the space, and it's the same for the whole space, right? And that's actually a pretty good mantra for what a manifold is. A manifold, here's a sort of slogan for it. Manifold is some space that locally looks like Rn. I mean, this is a n-dimensional manifold, right? This is the idea of a manifold. It's some space that locally looks like Rn. Now, usually, we're interested in smooth manifolds, right? Or at least piecewise smooth manifolds. The way I'm not being too technical just yet, but let's say we're interested in differentiable manifolds. I'll be vague. Differentiable manifold. And that extra baggage means it's a space that locally looks like Rn and supports calculus. So it's a space where you can do calculus somehow. All right. I won't really explain that today. That's one of the larger programs of our investigation in this course, is to understand how you can do calculus on a manifold. That's what First Steps in Geometry by McNerney does a decent job of getting us started on. That's a more technical thing to explain. But in the same way that we thieved the continuous differentiability theorem from Rn to norm linear spaces, we can do something very similar to steal calculus from Rn and lift it to a curve space through the appropriate mechanisms. It's not so much different than that picture we drew. Okay, but first things first. First, yeah. So there are two ways, there basically are two competing ways to describe a manifold. All right. If we're going to describe a, hey, no, is no allowed. You can go draw on those boards. This is not algebra. This is important. Here, go there. Sorry. Algebra is very important. I don't know what it's talking about. It's crazy. But this is like a 2-year event. Algebra is an every-year event. So I need to, this is my chance to say things like this that happens rarely here. Okay, so getting back to the point. The two viewpoints. Two views. Okay, so suppose M is an n-dimensional manifold. And I'll put quotes on that because I'm not being quite too strict about that. Manifold, let me not do that. Manifold in RQ, okay? The two ways to look at that are parametrically, right? We can either look at it parametrically. All right, so parametrically, we would describe the manifold. You've got some sort of, let's say, F, which is a mapping from, let's say, D, some subset of Rn, and it's going over here to RQ. So basically, f of D is equal to M. So in this case, the manifold is the image of the patch. I don't, let me make sure if I've used a different letter in the notes, let me try to shift and use that letter. You know how I am. I forget my letters. Uh-oh. I forgot my notes. So, yeah, this is a patch. I seem to have used R in the notes, so R is an awful strange, I don't care about that. F is better, whatever. So this F is sometimes called a parameterization, but I think that, I don't get joy from saying parameterization. I really like to say it's a patch. That's nice. So it's a patch. And yeah.
Does any constraint on any Q? Any constraint?
Well,
Like n less than Q?
I'm getting there. At the moment, this would allow for degenerate things, like F could be the zero map. That's not the right idea, though, right? It needs to be, we need something that captures that n dimensionality, right?
I mean, maybe map into smaller dimensions, but it will look like just two-dimensional.
Yeah, let's see here. So, generically speaking, a picture of this would be something like this is D, right? And then we're mapping it, to some kind of, here's F of D, right, over here in the big space.
So it would seem like in order to satisfy your definition of manifold, n would have to be less than or equal to Q, right? Because otherwise you couldn't have it look like it.
Yeah, I think that's fair. N would have to be less than or equal to Q. Let's not say that. Let's insist on something else. Let's insist that, to keep things relatively benign and also to, this will inadvertently rule out some examples, unfortunately, but just to keep things simple here, we'll basically assume, I have a definition in the notes with all kinds of careful this and that, but let me just say, what we want that F is continuously differentiable, at least on D and probably a little bit outside D to be safe. So let's assume that just to be safe, we want to assume that there's some kind of D prime where D prime contains D, and D prime contains D, and F is continuously differentiable on D prime. We want that. And then that's not enough, though, because that would still allow the zero map or a constant map or all kinds of other, well, zero map is a constant map. What we need is what?
It's invertible.
That's right. We need it's invertible. Now, here's the rub. That's exactly the right idea. I'm very, very happy you said that, because that's essentially what's needed to get the dimensionality, right? There needs to be some sort of F inverse, but you notice we don't really have the tool. We have an inverse function theorem, right? Which is for an n-dimensional vector space and another n-dimension. This is not the context of our inverse function theorem, right? So, but it is true that if we have, on the other hand, we can calculate, what's the Jacobian of F look like here? It's, partial F, partial x1, right? Partial F, partial x2, partial F, partial x, how many we got? N, right? But this is not usually a square matrix, right? Because it's more interesting when Q is not equal to N. If Q is equal to N, then we have an inverse function theorem, right? you need a more general theorem to treat this. There's something called the constant rank theorem that takes care of it. And basically the theorem is that I think if you pick a point, right, and if you can find a point at which, say P, and if you can get the Jacobian of f at P, if the rank of the Jacobian f at P is equal to n, then that proves that there exists a local inverse from the image of the map back to a neighborhood of that point. This is a slight general, well, it's a not so slight generalization of the inverse function theorem. Remember, the inverse function theorem assumes equidimensional domain and codomain. Right, but that's a consequence of our definition. We don't have to assume it. But you're right, n does have to be less than or equal to q, otherwise we cannot have rank n. That's right. Now, the question is, how do you find the rank of a matrix that's something you don't know, right? So the rank is simply the number of linearly independent columns or linearly independent rows. We can prove that they're equal, the number of linearly independent rows or columns. So if we have that independence of columns or rows, if there basically are 3 independent columns, that means that it's going to give us a 3-dimensional patch.
Okay.
So it's just that. Well, that's a funny thing in linear algebra. We learned that the number of linearly independent rows is equal to the number of linearly independent columns. It's part of the magic of Gaussian elimination. It's, but
So
I will.
that's why Q has to be at least n, because otherwise we couldn't have n.
Yeah. Q must be greater than or equal to n, clearly. Very good. So that is kind of a bare bones manifold in Rn. This is the parametric view of it. The other way to describe it would be what? What's the other way we could describe manifold? So let me give you an example of a manifold. Now, for manifold is a term which we use to intend to mean, you know, a space which doesn't have to be a particular dimension. We try to use this term to indicate things that are true for spaces of like multiple different dimensions. Of course, the dimension being fixed across the object, right? But things you can say about a manifold should be things you can say about a curve, a surface, a volume, a hypervolume, hypervolume. I mean, things we don't really have names for. But one thing we do have experience with, right, is a surface in R3. So let's just take a step back and look at that again. So like a surface in R3, right? What are the two ways? Like let's be more specific. Let's look at how about the sphere? Right? Sphere, radius R. What is the first thing we tell you in calculus 3? It is x squared plus y squared plus z squared equals to r squared, right? This is the sphere of radius r. Much later, usually, we talk about surface integrals, right? And there we learn that you can patch the sphere, right? Later, we learn, you know, you can look at S as being, how do we look at it? Something like, I usually use R or something, R of phi theta. How's it go? R sine phi cosine theta, R sine phi sine theta, R cosine phi, right? 0 less than or equal to phi, less than or equal to pi, 0 less than or equal to theta, less than or equal to 2 pi. You see, I've already violated my continuous differentiability because this is not a continuous function on the sphere because of the angle degeneracy. if you're being picky, it's not a patch on the sphere in that sense. We'll come back to that issue later, but well, let me just say now, if you want to get if you want to cover the sphere, you actually need two patches, one on one side, one on the other, and then that way you can have patches which are continuous. When you cover the whole sphere, you have this thing where you come back where you started with the angle, and in the mapping that makes a discontinuity because you're saying on one side you've got angle 0, on the other side you got angle pi. That, in an infinitesimal region, is not a continuity of the map. Yeah, it's like a seam. So to avoid those seams, you need two patches to cover a sphere. In fact, it's enough to throw out a pole. You can get a patch on the sphere modulo the north or south pole. These are called stereographic projections. We'll probably talk about these later. But, so this is the parametric viewpoint of the sphere, right? It's a mapping. We basically take this rectangle of angles, paste it onto the sphere in 3 dimensions. The other viewpoint is it's the solution set to this equation, right? These are very different viewpoints, right? Here, you give me a pair of angles. I feed it to the patch. It tells me a point on the sphere. Here, I give you an equation. You find some set of 3 numbers, which when you plug it in, it works. That's a point on the sphere, right? This is an implicit viewpoint, whereas this is an explicit viewpoint. So the other viewpoint is implicit. So implicit, you'd have something like g, right, which would be a function from, let's say, Rn cross R P maybe? Yeah. Going to Rn again, or R, I need to, Daniel, don't use the whiteboard markers to put stuff on paper, please. You have Crayola markers. Please use them. I only have finitely many of these that still work. Thank you. Ah! My counting is wrong. Let me cheat. So I'm looking at, here I do Rn. See, Rn. I always get stuck on the stupid counting here because I'm an idiot. Rn cross Rp to Rp again. Okay, but this P, what is this P? You know, this is supposed to be, I'm trying to set the universe to be RQ, the universe in which the manifold's living for our discussion. RQ is this thing, right? So Q is equal to n plus P, right? So if you want to write this without this artificial P, if we want to write this in terms of the manifold dimension and the ambient dimension, this should be G going from Rn cross Rq minus n to Rq minus n. And that helps illustrate the idea. Basically, here we have G of x comma y Maybe we need to go clothes shopping before we go home. Would you like that? Let's get nuts. I feel like I need to go find a new suit. I don't want to, but I'll do it. Keep it up. Let's see here. I can think of no more severe punishment for a boy of his age than to go clothes shopping from my own childhood. That is true. That is true. So g of xy equals to k, if and only if x and y are an element of the manifold. In other words, in this viewpoint, the manifold is equal to the inverse image under G of the singleton K. It's a level set of this set of this not one level function, but how many of them? N minus K. Q minus n rather. So in other words, we basically describe n-dimensional manifold. Let me just write it in words. Inside the ambient space matters here, RQ, inside the n-dimensional manifold inside RQ as the solution set of G of x comma y equals to k, right? And aka this is Q minus n equations, right? In how many unknowns? Q unknowns. For example, the surface up here, we have, this has G of x, y, z, is, x squared plus y, we could view it as x squared plus y squared plus z squared equals to r squared, right? So this, we have S is the inverse image of r squared. From the implicit viewpoint, it's the solution set to one equation, right? Because to get a two-dimensional object from in a three-dimensional space, we just need one equation, because 3 minus 1 is 2. Okay? Now, again, to be careful, we need to assume that this G is continuously differentiable, at least near the solution set that we're interested in, right? So assume there exists an open set on which the solution set is, and we need to assume it's continuously differentiable to avoid pathologies. And we also need to, we need something to ensure that these really are Q minus n equations. How do we do that? Daniel, stop. Out. Now. Come on. Just don't be touching my equations. Ay, ay, ay. Dang it, what was that? Ay, ay.
No, it's a manifold. Yeah, just.
Oh. Oh. Gosh. Stop it. Stop. Okay, so what condition do we need? What condition do we need that this actually be an honest-to-goodness n-dimensional manifold? It's something on the Jacobian, right? So we need that the Jacobian of G, right? We need that the rank of the Jacobian of G be what? And in fact, I mean, I was referencing an existence theorem, right, to say that there's a local inverse, but what we really need is that this rank condition is met over the whole patch. If there's even one point where that rank condition falters, that's going to be a point which is probably not, that's going to be a point where usually the case is that if you don't have that rank condition met, if we, if we don't have that ink, yes, if we should like that the rank of P, J of P is equal to n, we would like that to be true for all P in D, yeah. We saw this in like the Frenet frame stuff, remember? So this, in the Frenet frame, this appears as assuming that the curve is nonstop, right?
Why we couldn't have had the one-dimensional n-cube or s-cube pair.
Right, right. And then, well, there's more there. You need further data, as you pointed out. We need like things about the acceleration and other. It's more than just that for the Frenet frame to work, but that's inside baseball there. So here, I need that the rank of, what does the rank need to be of the equations? To make sure that how do you ensure that these n equations really are n equations? I mean, Q minus n equations. Right, I think this better be q minus n. If this is not q minus n, we're in trouble. Let's look at an example where we can see that trouble happening. Example, I finally have the good sense to not number them in here. So how about this? What's the equation of this thing? A cone, right? X squared plus y squared equals to z squared. We have a winner. And so this is a surface, except when it's not. And so g of x, y, z equals to x squared plus y squared minus z squared, right? The Jacobian here, g prime if you will, x, y, z is 2x 2y minus 2z, right? For that to define a surface locally, we need that the rank is 1. There's one point where the rank fails to be 1. The origin, right? This point right here, g prime of 0, 0, 0, is just equal to the 0 matrix, right? That has rank 0. Any other point on that cone is going to be placed with rank 1, which means that locally it's a surface. Which means I can put a patch on it also. Yes. And so this is a part of a larger class of things. If you have things that so yeah, suppose you got these like little cusps, but a finite number of them, right? But except for these few points, otherwise this thing's a manifold, right? A thing like this, a thing that's almost everywhere a manifold, but has a finite number of singular points, is called an orbifold. Cone, of course, is the most basic and well-known example of an orbifold. A lot of effort has been spent trying to understand how to put physics into the singularities of orbifolds. In some sense, singularities correspond to charges, and so the existence of these charges can be used to encode various physics. This is roughly the idea used in string theory, part of string theory. String theory is very large, right? Okay, so this is the setup. We can either describe it by a patch or by a system of equations, right? What? Students' homework, a whirlpool, and okay. What's the meaning here?
That's their homework.
That's their homework.
The steps in the boat to do for homework.
Oh, he's giving you homework. I get it now.
Alright, I'll give you guys your homework.
All right. I still have things to tell you guys today, obviously. And I think they're probably best illustrated with an example. So let's let M, all right, be described parametrically as follows. Actually, let me start with the equation. So let's suppose that it is g of x, y, z, w equal to, I don't know, x squared plus y squared, and then y plus zw, that's weird enough, equal to, let's say, 1, 2. All right, so this describes a typical point. X, y, z, w in M, right? Um,